Yeah, so welcome everybody to the International Seminar on Automorphic Forms. Today we have Francois Greer from Michigan State University that will teach us about Kudla's conjecture in cohomology for unitary Shimura varieties. Please, Francois.
Yeah, thanks very much, Ricardo, and thanks to the organizers for inviting me to speak. So, as Ricardo said, I'm talking about uh, Kudla's conjecture uh, in cohomology for unitary Shimura varieties, by which I mean the Shimura varieties attached to the groups U1N. Um, and maybe I'll just say right now, we can only do it for degrees in cohomology below the middle. So for higher codimension than one, but certainly not all codimensions. Okay, so just to set things up for the objects that I'm working with, let K be a imaginary quadratic field. OK is ring of integers. And I'm going to fix, for the whole talk, I'll fix this Hermitian lattice. Hermitian lattice, so that is an OK module equipped with a Hermitian pairing. With a Hermitian pairing that's valued in OK. And signature n plus 1 comma 1. So if this seems kind of strange, this convention, hopefully it'll become clear in a moment that I want to just have n reserved for the dimension of the boundary divisors in the toroidal compactification. Okay, and let me just assume for simplicity that it's self-dual. So meaning that L check is isomorphic to L. We don't need to assume that, but it gets me out of having to write all the Weil representation operators and the classes in the discriminant group. So yeah, just simplifies the notation. And for the rest of the talk, I'll also assume that I'll use gamma to denote the automorphism group of L. So some infinite arithmetic group. Okay, so the associated Shimura variety X will be a double quotient of U n plus 1 comma 1, so by its maximal compact on the one hand, and by gamma on the other hand. And so this is a Shimura variety of dimension n plus 1, and it's a ball quotient. And usually it'll be non-compact. With only zero-dimensional cusps in the Bailey-Borel compactification. So zero cusps in the boundary, indexed by gamma orbits of primitive isotropics, primitive isotropic OK submodules. J inside of my L, which must be rank 1 because of the signature. So rank 1 submodules. And so for each gamma orbit of an isotropic, I get a zero cusp in the Bailey-Borel compactification. So just to write that out, so X compactifies to the Bailey-Burrell, which is X union a finite collection of zero cusps. Okay, and this compactification is almost always singular, and there's a way of resolving it, or at least producing a Q factorial variety that's birational to X and proper. And this has the kind of lucky property that in this context of U n plus 1, 1, there's a unique choice of toroidal compactification. So there's no fan data required, or another way of saying that is that there's a unique fan in the corresponding cone. The corresponding cone is like just a copy of R. So this is X union with a collection of CM abelian varieties. One modulo finite groups. And there's one such abelian variety and finite group for each of the zero cusps. Okay. So I'll just say a few words about what these boundary divisors are. So these are the boundary divisors. And so, like I said before, they're going to be indexed by J. J up to the action of this gamma. And the way we describe them is you take J perp mod J, which is going to be a Hermitian lattice of signature n comma 0. So J perp mod J has signature n comma 0. And I can consider the abelian variety given by the Serre tensor construction. So J perp mod J tensor over OK with C mod OK. And I'll take G to be the automorphism group of the positive definite lattice. So this is a finite group. So I'm sort of eliding some slight technical issue here. So if the lattice, if the OK module here is free, then you just do this. And if it's not free, which can happen if your imaginary quadratic field has class number not equal to 1, then you have to do something slightly more complicated. But let me not give the details on that. Are there any questions so far about the setup? Okay. So these are these compactified Shimura varieties. And what I want to do is study generating series of special cycles. So we can define these generating series. Special cycles on X and then on X tor. Okay, so the first statement along these lines is very classical, and it goes back to Kudla-Milson. So I'll do the higher codimensional statement right away. So we fix G to be a codimension that's between 1 and n plus 1. So the dimension of the Shimura variety. And I'm going to take the sum over all non-negative gram matrices and M of the class of the special cycle Zm times Q to the M. So here M is a semi-positive Hermitian matrix. Okay, G by G, okay matrix. And this Q to the M really means e to the 2 pi I times the trace of y times m, where y is a coordinate on the Hermitian upper half space. So the theorem by Kudla and Milson says that this object is a modular form. More specifically, it's a Hermitian modular form of weight n+2, which is the rank of the original lattice over OK. So the series Kudla Milson is a Hermitian modular form. So this means that for the group, the split unitary group over Z, the Hermitian modular form of weight n+2, valued in complex codimension G cycles on X. So let me just, I realize now I didn't write what the definition of the special cycle is. So Z sub M underline is going to be the union over all V L, such that if I take the gram matrix, sorry, L to the G, I take the gram matrix for that collection of G vectors, it's equal to M underline. I take the span of V underline per inside this ball quotient. And then I need to quotient this by the left action of gamma. So this actually gives me a subvariety of X, provided that these vectors are linearly independent. This collection of vectors is linearly independent. And so just to handle the case where they're not dependent, you just make a definition that the class of this ZM underline is going to be the class of Z, the cohomology class of ZM, intersected with the appropriate power of the dual Hodge bundle. So C1 of Hodge bundle dual to the G minus the rank of this matrix. Okay, so if hopefully people are familiar with the orthogonal case or the codimension 1 case, this is just the natural way to generalize that to higher dimensional cycles, higher codimensional cycles, where instead of having positive integers, you have positive semi-definite Hermitian matrices parameterizing your Fourier coefficients. So the theorem that I want to talk about today, just joint with Salim Tayyou, is, as I said earlier, we have to fix our codimension between 1 and the middle dimension. So I think it has to be strictly less than the middle dimension, or 2. And the theorem is about the compactification of these special cycles. So if I take the sum, again, overall M underline greater than or equal to 0, of the class of the closure now of the ZM in XTOR, then this naive series is no longer a modular form, but it is a quasi-modular form. So it's a Hermitian quasi-modular form of weight the same as you expect from Kudla-Milson, valued in H2G of XTOR. So that's the first part of the theorem. Second part says that you can make a correction to this naive closure supported entirely in the boundary to restore the modular form property. So this series Q to the M minus some very explicit sum over the gamma orbits of isotropics. So this is just the summing over the cusps of some explicit J of Q. So these explicit correction terms are quasi-modular themselves, valued now in H2G of the corresponding boundary component. So that's what I mean by supported in the boundary, is Hermitian modular. Okay, so this is what we call the correction, the corrected Q series. So let me just kind of briefly say what exactly a quasi-modular form is in this context. So a Hermitian quasi-modular form is a certain holomorphic function on the Hermitian upper half space. So it's the same domain as for Hermitian modular forms, which admits completion So there's a kind of slightly confusing distinction between completions and corrections in this work. But so a completion just means a non-holomorphic function that's obtained from f by adding this completion term, so non-holomorphic. But which is modular. So it satisfies the usual modular transformation law under the action of integral points of UGG. Okay. But for us, this completion will kind of follow formally from a result of Rohrlich, but going back to Freytag. All right, so before I go into the proof, I want to just say what's already been done on related matters. So in previous work, so the divisor case is very well understood. So if you work not in cohomology, but in Chow upper one, even arithmetic, the corresponding statement is true, and by a result of Brunier, Howard, Kudla, Rappaport, and Young. And kind of in the other extreme direction, if you take, again, working in Chow, but working in Chow lower zero, so the top codimension, then the Kudla conjecture is known by the theorem of Brunier, Rosu, and Zemmel. Okay, so these are richer results because they're valued in Chow, whereas our results are valued only in cohomology, but it has the advantage that we can handle half the codimensions between 0 and n. Okay, so now I'll tell you exactly why we have to make that, we have to work in cohomology and not in Chow. So the key kind of lemma that we use that places that restriction on the result is, it's very simple to state. So if x and delta is a non-singular pair, so a non-singular variety with a non-singular divisor, effective divisor, and n delta, the normal bundle, to delta is ample or anti-ample, then the map that goes from homology of the complement of this divisor direct sum with homology of the divisor to homology of X is surjective. As long as K is at most the dimension of the divisor. And so for later, K will be equal to 2G when we use it on to prove the theorem. And the proof of this lemma is essentially just hard Lefschetz. So you write down the Meyer-Vittorius sequence for the covering of X by X minus delta, and then a small neighborhood, tubular neighborhood of delta, which is diffeomorphic to the normal bundle. And then you use the Giesen sequence for the punctured normal bundle. So the normal bundle minus the divisor. And then the desired surjectivity is going to follow from an injectivity of the next map in the Giesen sequence, which follows from hard Lefschetz. So then use hard Lefschetz for this delta and polarized by the ample line bundle C1 of n delta, which is going to be anti-ample actually in our case, but that just changes the sign of the Lefschetz operator. It doesn't actually change the injectivity or surjectivity of it. Okay, so I guess the takeaway point here is that hard Lefschetz theorem is really the tool that's being used, and hard Lefschetz gives you injectivity only in degrees below the middle. So that's kind of the central point. It's just not true for those other degrees. Okay. So that's what I call the splitting lemma. And then, so to prove the theorem now, so using the splitting lemma plus Poincare duality, which again is only true in cohomology, not in Chow, on this toroidal compactification, it will be enough to study the intersection product of our generating series, of our sum m bar zm bar q to the m with test cycles. So T that are homology classes in the complementary dimension. So, dimension equal to the codimension. So H2G X tor with Q coefficients. And this will, so the splitting lemma, what does it do? It allows us to reduce this to just a computation in the boundary. And we have a lot of understanding of the geometry of the boundary. The geometry of the boundary is much more easy to compute with than the actual geometry of the ball quotient, which is controlled by this mysterious arithmetic group. So this test cycle intersected with the series. So this test cycle can be written as homology class that's supported on the interior, plus a sum of homology classes that are supported on each of the boundary divisors. And so the first term T naught, which is a class supported on the interior, has intersection product that's the same as just the intersection product with the interior special cycles. And then we have these boundary terms, so sum over J of TJ, got it with oops. So notice that we do have the closure. We do have the Zariski closure there because we're really working in the boundary. Okay, so this first term, this first expression is a Hermitian modular form just by using Kudla-Milson as a black box. So this is modular by Kudla-Milson. And then these expressions can be computed pretty explicitly inside the boundary. So inside each boundary divisor component. Okay, so as I said earlier, so each delta J is a finite group quotient of e to the n, where E is just the elliptic curve that with Cm by OK. Okay, so this kind of packs two different finite group pieces into the story. So we have the automorphism group of the definite rank n Hermitian lattice corresponds to J, and then we also have the potential isogeny between C mod OK and C mod some other fractional ideal in OK. So I'll just deal with both of those slight imprecisions by just saying that it's delta J is a finite group quotient of e to the n. And e to the n is a very linear object, and we can just compute how the special cycles meet en. So the Zariski closure of the special cycle intersected with the boundary component pulls back to the following subtorus. So it's the sum over all G tuples of vectors now in J perp mod J to the G with Gram matrix equal to M of the span of those vectors perp inside of e to the n. Okay. And then we need to compute what is the intersection product with our test cycle. So Tj intersected with this sum over V G D bar UVM is just going to be a weighted theta function. So remember, J perp mod J is a positive definite lattice, so I can just write down the theta series, but I need to have a polynomial weight here. So P of V underline is a weighting function. So this is a weighted theta series. And the proof of this is a computation using the Serre tensor. So the Serre tensor, which is what I wrote down before. So the elliptic curve tensor with J perp mod J. And I guess what we realized is that these weighting functions have a very particular symmetry property. So P is a polynomial function in the real and imaginary parts of the lattice inputs, and then valued in Q. So it's a polynomial with the following transformation law property. So if I take my input vector V underline and multiply it on the right by a G by G matrix, then I just pull out a determinant, absolute value squared of the determinant of that matrix times P of V. So for any A in GLG Let's see. Okay. So as far as I'm aware, this property was first written down by Freytag, and a version of it was written down by Maas. So I've been calling these things Freytag polynomials, but I'm open to a better name. So these are special kind of polynomials from n by g matrices to q. These are Freytag polynomials, and they have a Laplace operator. Which sends them to Freytag polynomials with g1 smaller. So if I called the Freytag polynomials as above, fn comma g, then this Laplace operator takes me from fn g to fn g minus 1. Okay, so the theorem that appears in work of Roerich and older work of Freytag says that if P is harmonic, then this weighted theta function is a modular form of weight n plus 2. And if P is not harmonic, but it is annihilated by a power of the Laplacian, then we have the following correction. We have, completion. Sorry. We have the completion, which is the determinant of y inverse times the sum over v of exponential minus Laplacian over 4 pi of p applied to v underlined times y to the 1/2 q to the hvv. And this is a non-holomorphic modular form, and it transforms. So this is non-holomorphic. I'm using x plus iy to be my point in the Poincare space, non-holomorphic of weight n plus 2. Okay, so this theorem just out of the box implies that the generating series that we get are quasi-modular forms. Just to go back one step, it's enough to prove that if you after intersecting with any particular test cycle, you get a quasi-modular form. We can write our test cycles as something supported on the interior plus something supported on each boundary component. The interior term is a modular form, and the boundary term is a quasi-modular form, just by writing down exactly what it is in terms of this weighted theta series that will depend on the test cycle that you're using, and of course which boundary component you're computing in. So what j perp mod j happens to be there. Okay, so that finishes. That's the proof of the first part of our theorem. So next we want to talk about the correction. So for the correction, corrected Q series. We essentially we want to know how far this polynomial is from being harmonic. So we need to know how far this polynomial weight function is from being harmonic. Because remember, by this criterion of Roerich and Freytag, if the weighting polynomial is harmonic, then there's no correction is needed somehow. It's just already a modular form. And if it's not harmonic, then then sort of the failure is exactly dictated by how many applications of the Laplacian you need in order to get zero. So it turns out that the answer to this is quite nice, and it just depends on the test cycle t. So it only depends on where this Tj sits in the Lefschetz decomposition. Of H2G of this particular boundary divisor, which up to finite group actions is going to be isomorphic to homology of this power of the elliptic curve. Okay, so this is completely understood. So what the Lefschetz decomposition is. So just to remind you, so what is a Lefschetz decomposition? So you need to have a smooth projective variety with a polarization. So C1 of the normal bundle of this boundary divisor is anti-ample because this boundary divisor admits a contraction to a point in the Bailey-Borel. So if I just take the dual normal bundle, this is now an ample. It's an ample on delta. So it pulls back to a polarization, I'll call it theta, on this power of the elliptic curve, of the CM elliptic curve. And this polarization is equal to a positive multiple of the polarization that just comes from the Hermitian form on J perp mod J. Okay, and so this positive constant essentially is some generalization of the width of a cusp, so the width of the cusp. Okay, so the main computation that we did is the following. So if we consider the sum from g equals 0 to n of hgg e to the n, so these are Hodge cycles in this CM abelian variety. There's a natural map from here to the Freytag polynomials, which is just given by taking a certain test cycle to the polynomial weight that you get when you intersect it with special cycles. And the theorem is that, first of all, this is an isomorphism. It's isomorphism. And it intertwining the SL2 representations on both sides. On both sides. Okay, so what are those? So this is what I mean when I say the Lefschetz decomposition. So there's an action of SL2 on the full cohomology of any smooth projective variety, and it preserves the Hodge decomposition. So in particular, it gives you a representation just on the sort of central column in the Hodge decomposition. So the lowering operator, because I've written this in homology, the lowering operator is going to be cap product with the polarization. And the raising operator is just its adjoint with respect to the Hodge star. And the Hamiltonian in this case is just G minus 2n. And the lowering operator on this side is the operator I mentioned earlier, which is this Laplace operator. And the raising operator, we define it in our paper, and some version of it appears in old work by Shimura, but in a slightly different context. So I'll just call it the Euler operator, and the Hamiltonian is the same. Um, and so then, okay, so we have this isomorphism. And the Lefschetz decomposition just means the decomposition of a representation, an SL2 representation into isotypics. And so the Lefschetz decomposition on each side are going to match up, of course. This is an isomorphism of representations. And the next thing is that we have this map. We have a linear map that we'll call theta that goes from Freytag polynomials to quasi-modular forms. So Hermitian quasi-modular forms in this case of weight n plus 2. And this is just where we sum up over the lattice. So we take a Freytag polynomial to the sum over all v and j perp mod j to the g of p of v q to the h v v. Okay. And so the Lefschetz decomposition, or at least the Lefschetz filtration, maps under this map to the what's called the depth filtration for quasi-modular forms on Q Herm. Okay. So the cycled value, so the original cycled valued generating series of closures Q to the M underline pulls back to a very natural element of HGG e to the n tensored with Freytag polynomials. So this is just the map from H lower GG e to the n to the Freytag polynomials that we had earlier. And because the map above is a map of representations, this particular element is annihilated by SL2. So that's just a fancy way of saying that if I have an element of this tensor product, it's the same. If I apply an element of SL2 to the left-hand tensor factor, it's the same as if I apply it to the right-hand one. So it's just a map of SL2 reps. And so we can express this element. I'm going to call it alpha. We can express alpha as a sum of its Lefschetz components. And because we're in a particular weight, there are universal projectors onto the Lefschetz components, which live in the universal enveloping algebra of SL2. So, so there are universal projectors in the universal enveloping algebra of SL2 onto each such component. And because I'm interested in elements in the sort of shallowest stratum of the Lefschetz decomposition, I'll only write down the projector onto that one. So it's the primitive projector. So I'll call it pi prim. And the formula for it, not too hard to derive by sort of inverting the rule for how SL2, how raising and lowering operators act on these different Lefschetz components. It's m plus 1 factorial over j factorial m plus j plus 1 factorial e to the j f to the j, where m is just short for n minus 2g. Okay. So you just apply the projector onto the zeroth Lefschetz component or the primitive component, and that gives you your correction. And you can be quite explicit about what these corrections are, because each of the e to the j and f of the j, f to the j are actually operators on these Freytag polynomials. So if you choose an explicit basis for hgg of e to the n that's adapted to the Lefschetz decomposition, then you can couple each of those basis vectors with a corresponding Freytag polynomial that you can write down using this formula and the SL2 action. That's how the end of the proof goes. And the last thing I want to do is say a few words about the orthogonal case, because it's very similar in many ways. But there's one important difference. So this is still kind of work in progress. So a few words about the orthogonal case. So in the orthogonal case, so meaning instead of a unitary group, you take a U or O2 comma N. So the toroidal compactification of D mod gamma, of course, depends on the fan in a major way. So let me just take the type 2 partial compactification. So here it's non-compact still, but somehow you've replaced each of the one cusps with a Kuga-Sato variety. And this pair satisfies the splitting lemma. So the relative version of the splitting lemma before. So the same technique can be applied in that setting. I guess maybe I should put O2 comma n plus 2 here, so that the boundary becomes e to the n. So delta j is now a finite quotient of e to the n, where e is now the universal is a modular family of elliptic curves. And so the key difference between the orthogonal and unitary cases, from my standpoint, is that the analogous definition of Freytag polynomials, so the orthogonal versions of these Freytag polynomials, are global sections of a standard bundle on a Grassmannian. So it's just global sections of O of 2 on the Grassmannian Gn. And okay, you can describe these explicitly as we did earlier. So you can think of these as polynomials P from Q to the n by G to Q, such that P of VA is, this time there's no complex conjugation. It's just determinant of A squared times P of V. But the key difference is that this is no longer isomorphic to even the algebraic cycle classes in the boundary. So you have a surjection from HGG of e to the n q, but it's not an isomorphism. So it's not an isomorphism as soon as G is at least 2. So this has a kind of a funny corollary, which is that there are cycles that are orthogonal to all special cycles in the boundary. So there exist cycles Tj in the boundary that are orthogonal to all the ZM underline bars. Okay, so that's not true in the unitary case because we have this isomorphism between Freytag polynomials and the Hodge classes in e to the n. But in the orthogonal case, there are just more, there are few orthogonal Freytag polynomials. So yeah, maybe I'll stop there. I mean, I can say a few words about the type 3 part, but that's really in progress. So maybe I'll just answer any questions that you might have. So thanks for your attention.